Physicalism is the framework within which causality is understood by most scientists and philosophers of mind, and it's the framework that I will adopt here. Physicalism maintains that there's only one fundamental substance or substrate, namely physical matter or energy, changing within space-time, in a manner that is best described by the laws of physics. Physicalist stances fall into different camps. One division occurs between deterministic and indeterministic versions of physicalism. Determinism essentially asserts that there's only one possible future course of events, whereas indeterminism asserts that there are many possible future courses of events that might occur at any moment, perhaps with different likelihoods, even when only one actually occurs. Another division lies between reductive and non-reductive versions of physicalism. My own views are non-reductive and indeterministic. For centuries following Newton, causality was understood in terms of a colliding billiard ball model of particles, based on the idea of energy transfer among particles that obey the laws of classical mechanics, including the fundamental laws of conservation of energy and momentum. Fundamental particles were assumed not to transform into different fundamental particles. Particle trajectories were thought to be entirely determined by physical properties such as mass and momentum. This energy transfer conception of causality was deterministic. Pierre Laplace argued that if a demon could know with absolute precision the locations, masses, momenta, and all other physical properties of all elementary particles everywhere, the whole future and past of the universe could be, in principle, known to it. This is not only impossible in practice, it's impossible in theory, because such a demon is himself a part of the universe and would have to know about the physical basis of his act of knowing and then the physical basis of that act of knowing and so on, which leads to an infinite regress. So Laplace's demon argument can't work. This raises the worrisome problem that it might not be knowable whether the universe is deterministic or not. With the advent of modern chemistry, greater attention was paid to how energy undergoes transformations and exhibits new properties as fundamental particles combine and recombine in chemical reactions. Even though this energy transformation conception of physical causation was no longer a simple Newtonian billiard ball conception of particle collisions, it remained in essence deterministic. Physical causality was thought by most scientists to be fully or very nearly fully described by the laws of classical physics and chemistry until approximately the turn of the 20th century. These laws described how energy was transferred among particles and fields and how energy was transformed through chemical reactions. The first hint that the fundamental laws governing particle behavior might be probabilistic rather than deterministic arose with the realization that closed systems tend to approach equilibrium. For example, if water at one end of a bathtub is hot and at the other end is cold, the two will tend to mix with each other with a much higher probability than the probability that they will remain segregated. The second law of thermodynamics implied not only that nature might be probabilistic, but that time might have a directionality that contradicts the temporal reversibility implicit in classical mechanics. However, thermodynamics could still be regarded as an instance of epistemological rather than ontological indeterminism, in that underlying particle behavior might still be entirely determined by the physical properties of particles and forces acting on particles, such that at each instant a particle has only one possible path open to it. Remember, epistemology refers to how we know things, whereas ontology refers to what really exists. An epistemological indeterminist would maintain that it is only because we cannot obtain complete knowledge of these properties that we must be satisfied with higher-level probabilistic laws such as the laws of thermodynamics. Not until the development of quantum theory were the physical properties of particles regarded as ontologically indeterministic by many, if not most, physicists. In the famous double-slit experiment, photons, or particles of matter like electrons, are shot through two slits, one at a time. They land on a photographic plate and make a diffraction pattern. Thinking classically, one would think that a point-like particle would have to pass through either one slit or the other. But if that were the case, then we would not get a diffraction pattern on the photographic plate. The key insight from the double-slit experiment is that a particle must, in some sense, have wave-like properties in order for it to be able to interfere with itself. This can be thought of as a probability wave that passes through space, where the magnitude of the wave at a given location and time indicates the probability of, for example, the detection of a particle upon measurement at that location and time. This is a very strange and non-intuitive view of what is real. Under this view, there are ontologically real possible paths open to particles, and these possibilities in some sense interfere with each other. Despite the strong empirical evidence for this kind of quantum domain strangeness, and there are many, many other bizarre examples, determinists did not simply concede that nature, as Einstein put it, plays dice. He and other physicists argued that the fundamental level of causation must still be deterministic, despite the probabilistic character of quantum theory. According to advocates of such hidden variables determinism, the probability density functions whose dynamics are given by the equations of quantum physics describe uncertainty in our knowledge of particle locations and movements, not any kind of actual non-specificity of particle locations, momenta, energy, or durations. The dominant Copenhagen interpretation of quantum mechanics, framed by the physicist Niels Bohr, however, regarded uncertainty concerning measurement outcomes to be a fundamental fact about reality rather than simply a problem concerning the limits of our knowledge about particle properties. John Stuart Bell argued against Einstein's deterministic view that no physicalist theory based on local hidden variables could account for quantum-level effects. He proved mathematically, and many subsequent experiments have confirmed, that any local hidden variables version of quantum mechanics can be ruled out, and that allowable versions of quantum mechanics must either allow for non-local coordination or correlation of the states of distant physical events, or certain properties, such as momentum or position, must lack a definite state, even when they are not measured and are not known. Since determinists are loath to give up the idea that unmeasured properties nonetheless occupy a definite state at each moment, even if that state cannot be known to us, versions of non-local hidden variable determinism have been proposed. Perhaps the best known of these was proposed by David Bohm. According to this interpretation of quantum mechanics, particles continually coordinate with all other particles in the universe instantaneously. Extensive empirical evidence supports the reality of non-locality. This implies that events here and now might be correlated with events light years away, lying outside of our light cone. Reality is clearly much stranger than it appears to us. Although maintaining a belief in determinism may require accepting the reality of non-locality, that non-locality is the case is not sufficient to prove that either determinism or indeterminism is the case. That said, non-locality is a logical consequence of Heisenberg's uncertainty principle. According to Heisenberg's uncertainty principle, there is a fundamental limit to the precision with which certain complementary pairs of physical variables of a particle can be known. For example, one can know with great precision the energy of a particle-level event, but then will lack certainty about the timing of that event, and vice versa. Or one can know with great precision the position of a particle-level event, but then will lack certainty about the momentum of that event, and vice versa. The reason for this is the so-called quantization of action. Action, which has the units of energy time, comes in smallest clumps. It is because of the quantization of action that atoms have electron orbit shells allowing atoms to exist. So the universe as it is, with its many types of atoms, is deeply rooted in the quantum domain's strangeness, in particular in the quantization of action. In sum, I am an indeterminist because quantum domain events have more than one possible outcome, any of which might really happen. For example, in the double-slit experiment, the photon or electron might land here on the photographic plate with some non-zero probability, and it might land there with a different non-zero probability, and whether it lands here or there, conservation of energy and momentum and all the other laws of physics will not have been violated. Going forward, I will accept the weight of empirical evidence for modern physics and assume ontological indeterminism to be the case. A central problem for us will be whether events in the brain can harness quantum domain indeterminacy such that it makes a difference in neural and mental processing. We'll get into this when we get into neural processing.